All right. So we'll go ahead and get going. We'll start today, like I'll try to start every day, in which I'll ask, do people have questions on what what they've looked at online in the lecture videos and lecture notes and textbook, what we covered last time, or anything of that nature, questions about the course as well, how things will be done. And for those who are coming in or just came in, make sure you pick up one of these. I have some up here. Otherwise, they're also by the back door by where we entered, for your participation grade for the day. I will typically bring, or not typically, well, bring one of these every day, and I'll try to get here before everybody to leave it on the table by the door where you enter. Yeah. And again, those who are on Zoom, feel free to ask questions as well, either through chat or otherwise. So no one has any questions about anything so far. All right, then we will get going on more example questions, more problems related with identifying intermolecular forces. Okay. So this very first question here, we want to rank these 5 different molecules from lowest to highest boiling point. So I'll first give you guys a little bit to kind of think about this yourself, discuss with those around you. Okay. But as you're thinking about it, just first think about how boiling point relates to the intermolecular forces, whether or not a higher boiling point is at stronger intermolecular forces or weaker intermolecular forces. So we'll also vocalize this question and answer just in case, for those who might not be able to read what's been typed up there. But there's a question about, right, if you're attending on Mondays, are there online versions of questions for today that you need to take? Or if you're attending Wednesdays, or online questions for, you know, when you're attending the class online on Monday, right? And the answer is no. If you're attending class, right, on Monday or Wednesday, echo itself. Sure, everyone's muted. Like, all right. right? If you're attending on Monday, you just take the questions on Monday, and that counts for your full participation credit. If you're attending Wednesday, right? Questions you guys receive on Wednesday will count to your full participation credit. And those who are taking the class online only will get questions posted weekly. I haven't posted this week's questions yet, but they will be up soon on Canvas, and you'll take those to receive your participation points. Okay? All right. So for this example here, we have a bunch of different substances. So the first question we ask ourselves is, right, if I want to have increasing boiling point, right, I want to think of what has the highest boiling point. That substance is going to have the strongest or the weakest intermolecular force. For higher boiling point, you're going to have stronger or weaker forces holding itself together. Stronger, right? If you have strong intermolecular forces, it takes more energy to break the molecules apart into the gas phase. So stronger intermolecular forces means higher boiling point. Okay? And so how we want to list these things is weakest intermolecular force on the left, the strongest intermolecular force on the right. Okay? So the weakest over here, strongest over here, right? And so when we look at these guys here, the weakest is going to be H2 here. H2 only has dispersion interactions, and it's also an extremely small molecule. Okay? So it's going to have very, very weak intermolecular forces. It's going to have a very, very low boiling point. Boiling point for H2 is in the like Kelvin scale or something like that, single Kelvin, 10 Kelvin or something like that. I don't know off the top of my head, but very, very, very cold. Okay? Right? Neon is a molecule, or in this case an atom, that only has dispersion intermolecular forces. So that also, right, is going to be very weak intermolecular forces and have a very low boiling point. So we're going to go hydrogen gas, then neon, right? So D or E potentially here. And then we look at some of the other molecules left. We have barium chloride, carbon monoxide, and hydrogen fluoride. Barium chloride is a salt, right? It is an ionic compound, so you don't have intermolecular forces holding this together. You actually have ionic bonding holding this together. So that's significantly stronger than any intermolecular force. So that is going to be the strongest and have the highest boiling point. And then the question of CO and HF. Both of those molecules have dipole-dipole interactions because they're polar bonds and they're non-symmetrical molecules. But HF has hydrogen bonding forces because they have hydrogen bonded with a fluorine, right? And so HF is going to have a higher boiling point than CO. So D here is the list from weakest, lowest boiling point, weakest intermolecular force, to strongest forces, highest boiling point. Okay. Questions? All right. Okay, the reasoning for neon again. Yeah, so for neon, again, neon has only dispersion interactions, right? It has no bonds. It's just an atom. So it can't have dipole-dipole forces. Obviously, it can't have hydrogen bonding and so on, right? So it's just an atom, but neon is more massive than hydrogen. And so that's why it's got the stronger dispersion interactions than hydrogen, right? Dispersion forces increase with molecular weight, with molecular size, right? And then if you have two molecules with similar molecular size, right, you have stronger dispersion forces the more linear the molecule is versus the more spherical the molecule is. Okay? All right. So which of these molecules will have dipole-dipole attractions between themselves, right? Between CO2 with CO2, PH3 with PH3, C10H20 with C10H20, so on and so forth. Anyone feel comfortable with what they feel is the molecule with dipole-dipole interactions amongst this group?
Would it be the carbon tetrachloride?
So carbon tetrachloride does have polar bonds, right? Carbon and chlorine have very different electronegativities. Those have polar bonds. But in the case of carbon tetrachloride, the structure of that guy is symmetrical. I'll draw it out here. So, right, in the case of carbon tetrachloride, you have this structure here where you have these polar bonds, right, where electrons are being drawn to the chlorine from the carbon, right? Just kind of how I'm drawing these arrows. But those arrows all sort of kind of point in opposite directions of each other and cancel each other out. And so this won't have any net dipole. But I saw it typed up in the chat as well, pH3. This molecule looks like this, which will have polar bonds, right? Moving this direction, and there's some lone pairs on the phosphorus, right? And this will have a net dipole, okay? Kind of pointing in up direction with how I've drawn this, but that will have a net dipole, right? And if we do some of the other molecules, let's actually keep here, right? So for example, CO2 has this structure, right, at CO2. So again, this is going to have polar bonds, but these polar bonds are pointed in the exact opposite direction of each other and cancel each other out. And so CO2 will not have any dipole-dipole interactions, right? Just like CCl4, okay? And Br2, there's no polar bond, so that will not. And then the C10H20, anytime you see these like carbon-hydrogen compounds, they're not going to have dipole-dipole interaction. If there's some oxygens or nitrogens thrown in, then they will have dipole-dipole forces. But if it's a pure hydrocarbon, just hydrogen, carbon together, right? In this case, it's decane, right? If it's pure hydrocarbons, then there will be no dipole-dipole forces, and it's just dispersion interactions. And so in this case, pH3 is the molecule that will exhibit dipole-dipole attractions between other pH3 molecules, right? The rest of these four molecules, CO2, C10H22, CCl4, Br2, all have just dispersion interactions as their predominant intermolecular force. Questions? I'm trying to do a number of examples of these because some of these things, especially things like, right, like CO2, CCl4, those are examples of molecules, right, that have polar bonds that you'd expect maybe would have dipole-dipole forces, right? And we have to kind of think more about the structure to determine whether or not they do or don't. And so I want to do a lot of examples of these things to hopefully get us more familiar and more comfortable with identifying when certain molecules have dipole-dipole attraction with each other. Okay. So in this case, we're wondering which molecule or molecules potentially have only dispersion forces as its intermolecular force, right? So it doesn't have dipole-dipole, no hydrogen bonding, no nothing but dispersion as its main type of intermolecular force that it exerts. Okay. And again, for any type of questions we're doing here in class, you're always welcome to discuss with other people if you feel like it. If we weren't trying to do all this social distancing, things like that, I try to have more group interactions, but because of that, I don't really want to do that because it kind of defeats the purpose of why we split the class in half, blah, 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 blah. So yeah, so let's just talk, right? So I have a number of suggestions here over Zoom. Seems the kind of dominant is CH4 here. People think only has dispersion interactions. So we'll go through these molecules one at a time. Let's talk about hydrogen chloride here. So hydrogen chloride, what type of intermolecular forces is it going to have, and what's its most dominant intermolecular force, I should say? Yeah, for HCl, hydrogen chloride. Yeah, so in this case, there will be dipole interactions. If it's broken apart in solution, it will be apart in hydrogen ions, chlorine ions, and we'll have ion dipole. But in this case, since it's just a neutral molecule interacting with other neutral molecules, so in all of these questions, a lot of times it's not properly worded in my part sometimes, or for other places that write these questions, but right, what's asking, right, it's if you have an HCl molecule and another HCl molecule, right, how do these interact with each other? So in this case, right, we have no ions, right, but we do have polar bonds, right, that exist. And so if we have these polar bonds in these molecules, right, and it's linear, right, it's not symmetrical in terms of that polar bond, right, then this will have what type of intermolecular force? Dipole-dipole. Yep. So HCl, strongest intermolecular force, or dipole-dipole interactions. The next is NaCl. Now, this, it's not really a proper question to ask what's its stronger intermolecular force, right? Because it doesn't have intermolecular forces, it has ionic bonding, right? This is another example of a salt. So NaCl is just ionic bonding. It's not any type of intermolecular force. So, right, Olivia, you are correct, right? That ionic bonds don't have intermolecular forces, right? They have ionic bonds that exist, right? These are strong intramolecular interactions, not these intermolecular interactions that we're talking about. Okay. Then CH4Cl, right? This molecule is going to have what type of intermolecular forces? Or CH3Cl, I think I said CH3Cl here.
Dipole-dipole.
Yeah, dipole-dipole, intermolecular forces, right? Because again, they're polar bonds, and specifically the carbon-chlorine bond is polar, and it's not the same, right? It's not symmetrical with the carbon-hydrogen bond, right? So this will have dipole-dipole forces, the CH3Cl. CH4, we have polar bonds, but they're all symmetrical with each other. They're all the same, cancel each other out. And so for CH4, we only have dispersion intermolecular forces, okay? And so CH4 is the molecule with only dispersion forces. And then finally, C6, H13, and H2. What's going to be the strongest intermolecular force there? Hydrogen bonding, right? It's going to be hydrogen bonding because I have a hydrogen that's bonded to nitrogen, okay? Now, there's also dispersion interactions because, it's a large molecule, a bunch of carbon hydrogens floating around, right? But the strongest intermolecular force that exists in this molecule is that hydrogen bonding that exists because of the nitrogen-hydrogen bond in this molecule. Okay? So CH3Cl, right? The question was, what is the strongest intermolecular force for CH3Cl? That is dipole-dipole, right? Again, if we draw that molecule, we can draw it right like this. And again, there's these polar bonds, right, where the arrow points to kind of where the electrons are being drawn to, because these are the more electronegative atoms. Cl is more electronegative to the carbon. So that arrow, right, is pointing to the fact that electrons are being drawn to chlorine. So the electrons are kind of being drawn upwards towards the chlorine. So this has a dipole moment, right, that points towards that chlorine molecule in this CH3Cl molecule. So it will be dipole-dipole. Okay. Other questions? All right. Now here we have some examples of, in these cases, what we're asking for is what are the inelectric forces between Br2 and CCl4, or Na plus and CHCl3, H2O and NO, so on and so forth, right? So we'll do this one at a time. So Br2 with CCl4, what type of intermolecular forces exist between those two molecules?
Dispersion.
Yeah, dispersion intermolecular forces, right? So in this case, right, Br2, no polar bonds, and CCl4, as we've talked about, right, has polar bonds, but they're symmetrical. So neither of these have dipole-dipole interactions. There's definitely not any hydrogen bonding, right? There are no ions, so there's no ion dipole, right? So it's just dispersion intermolecular forces that exist between Br2 and CCl4. And what about Na plus and CH3Cl?
Ion dipole.
Yeah, ion dipole, right? Because we have an ion, Na plus is an ion, and then CH3Cl has a dipole, right? It has polar bonds that are not symmetrical because CCl is not the same as CH, right? The CCl bond and CH bond are not the same, so those are not going to be symmetrical. And so that is going to be ion dipole for Na plus and CH3Cl. And then H2O and NO.
H bondings. Hydrogen bonds.
So hydrogen bonds, right? So in this case, right, you have water, right, has hydrogen bond with oxygen, okay? And then NO here, right, will, sorry, NO, right, has a dipole moment as well as lone pair electrons, right? So NO can kind of hydrogen bond in some way with the water, right? So it's not able to kind of reciprocate, in which case, right, like H2O with H2O, right? Hydrogens are having this hydrogen bond interacting with oxygens on other water with each other, right? Not quite the case here, but yeah, there is hydrogen bonding between H2O and NO, and there's also dipole-dipole interactions between the H2O and NO as well, right?
Oh, okay.
And then CH or C4H10 and CH2O.
Is it like dipole induced dipole?
That's getting a little more advanced than actually some of the things we're talking about. But yeah, there is the dipole can induce a dipole. The dipole on CH2O can induce a dipole on C4H10. We're not going to really cover and talk too much about that in this course, but that does in fact happen. And so here it's more what we're looking at is, let me write this out. right, so we have C4H10 and CH2O. Right, this only has dispersion forces, right? In C4H10, there's only dispersion forces. For CH2O, we have dispersion forces and we have dipole, right? Dipole-dipole interactions, right? In C2H2O, right? Because C2H2O has this structure, HO, right? This is a net dipole, right? So there's dipole interactions and dispersion interactions for CH2O, only dispersion for C4H10. So for the sake here in this class, what we categorize this pair as having only dispersion intermolecular forces between each other. Okay. So if we were to ask what type of intermolecular force exists between these two molecules, I would say dispersion interactions. Okay. There is such a thing as dipole-induced dipole intermolecular forces, but again, we won't really talk about that or focus on that in this class. So for the sake of this class, mainly we're referring to kind of just dispersion interactions. Okay. And then finally, NH3 with HF. Yeah, hydrogen bonding, right? You have hydrogen bonding that exists in NH3, and you also have hydrogen bonding that exists in HF. Okay. And so these will have hydrogen bonding, right? And technically, it also have dipole-dipole and dispersion, right? Hydrogen bonding being the strongest intermolecular force that exists between these two molecules. Questions?
What did you say H2 and NO was again?
All right. So if there are no other questions about some of these examples that we started off today with, then we'll kind of move on to some other topics in this chapter. Okay. All right, so talk a little bit about phases, phase changes, and phase diagrams. Okay. So right, we have our solid, liquid, and gas phases. You can have different phase changes between these. The red lines here indicate what are called endothermic processes, right? Endothermic meaning it takes in energy. Energy is required for these things to occur. The blue lines indicate exothermic processes, right? Meaning they give off energy, okay? That's why steam water hurts so much, is not so much the heat from the steam, but more when the steam hits your hand, that gas condenses on your hand and forms water, and that condensation of that gas into a liquid on your hand is what causes you to potentially get burnt by steam, okay? This is a very exothermic process going from gas to liquid. Again, it's condensation, okay? Right, liquid to solid, freezing is exothermic, right? Deposition, going from a gas to a solid, exothermic, and then the other processes are endothermic, right? Melting is endothermic, vaporization is endothermic, and sublimation is endothermic, right? All right. For those on Zoom, so Jason, right? So H2O and NO, right? There was some hydrogen bonding and others. Was that asked earlier and I just missed the question? Maybe. I don't know if Audrey asked that question was answered, but yeah, hydrogen bonding interactions between the H2O and NO because of the hydrogen bonding that exists in H2O. The lone pairs on the NO, but there's also dipole-dipole interactions as well that exist. Okay. All right, so those are a type of phase changes. Okay. Right. This question here is related to some stuff in the lecture, some of the lecture videos related with this, right? In which I have some unknown substance. Okay. I know that the heat of sublimation of that substance is 50 kilojoules per mole, and the heat of fusion is 3 kilojoules per mole. And my question is what is the value of the heat of vaporization? Right? When thinking about this problem, right, if you're not sure what the relationship between these things are, think about what sublimation is, what changes in state we're incurring, right, for sublimation, going from what to what. For fusion, we're going from what to what, and then from vaporization, we're going from what to what. And trying to then relate those three changes. All right. So first, let's just think about these phase changes. Okay, so sublimation, right, is when you go from a gas to a solid, right? Fusion was liquid to a solid, and then condensation is from a gas to a liquid, right? So if I want to go, right, and this is what we're interested in, okay? But if I want to relate these three things, right, I think about sublimation goes straight from a gas to a solid, okay, right? Well, fusion and condensation eventually go from a gas to a solid. You just have this intermediate step of a liquid along the way, right? And so, right, to get the relationship between these guys, right, it's the fact that that heat of sublimation is just equal to the heat of fusion plus the heat of condensation, right? Right? In the end, right, if you undergo condensation and then fusion, you do the same overall change in state as sublimation. It should be a B, not a P. Right? And so we want the addition of these things, right? And so if you fill in what we're looking for and what we are given, we're told this was 50. I think I used units of kilojoules per mole, right? And then we were told this was 3 kilojoules per mole. And then we're looking for enthalpy of condensation. Okay? And so you just subtract 3 over. Answer, right? Oh, I put vaporization here. Okay. So that should have been like probably condensation because it's opposite direction. Right, sublimation, right, is, oh, no, I just completely messed up, right? Sublimation is solid to a gas. I put fusion with solid, or liquid to solid, sorry. That was a misstep on my part. My apologies. Yeah, no, I had everything right in this slide. I just had a little bit of a brain freeze, right? So going back to this, this is a poor job on my part. Fusion, right, always trips me up. Fusion always messes me up because I always think things fusing together are forming a solid in my head, but it's the opposite of that. It's a solid going to a liquid. Fusion, which same thing as melting. So I apologize. Yeah. Right. So this relationship still is true. And then we're not talking about, in this case, we want a liquid to a gas. So we want to look at vaporization, right? So that liquid to a gas. I should have just rewritten this entire thing, but yeah. Right. Combination fusion and vaporization. All right. But, right. So B here, 47 kilojoules per mole is the answer. Because again, the energy it takes to go from, say, gas to solid or solid to gas, right, is the same as doing it at going through the liquid phase, right? You're just breaking that overall term into two smaller pieces and then adding them together. So yeah. Again, B here, 47. All right. So let's talk about vapor pressure. Okay. This relating to phase changes and boiling points and so on. So what is vapor pressure? Right, vapor pressure, right, is the pressure exerted by some gas in, say, like a closed container, right? So in this apparatus, you have an empty container, you put in some liquid. What happens is some of those liquid atoms or molecules go into the gas phase that are on the surface. They bounce around in the gas phase, and eventually some of those gas phase molecules can hit the surface of the liquid and condense back down into the liquid phase. And you eventually reach an equilibrium where you have an equal number of liquid atoms going into the gas phase as you do gas atoms going into the liquid phase. And you reach this state of equilibrium where you have some net number of molecules in the gas phase, and those molecules in the gas phase exert a pressure, and that pressure is referred to as the vapor pressure of the liquid, right? Now, if you have a liquid, right, that's in an open container, you'll never really, feel the exertion or see this vapor pressure because, right, those gas phase molecules just escape and go out into, everywhere, right? And that's how you get, right, liquids that evaporate, right? Is because, right, you have a pool of water sitting on a surface, right? Eventually it goes away because on that surface, molecules are getting into the gas phase and it's in an open container, so those molecules are never coming back, right? So they eventually evaporate away completely and your liquid goes away, right? But in a closed container, those gas molecules are trapped and eventually reach a state of equilibrium and exert some amount of pressure within that container that's related with the number of molecules in the gas phase. Okay. And so, related with this, right? So if I had two different molecules, one molecule has very, very strong intermolecular forces, and one molecule has very, very weak intermolecular forces, which molecule do you expect to have more atoms in the gas phase?
The one with the weak ones?
Yeah, so thank you. The one with the weak ones, we would expect to have more atoms in the gas phase, more molecules in the gas phase, right? Because to get into the gas phase, they got to break apart from each other, right? Right, these intermolecular forces are what are holding the molecules together, right? If I want to go into the gas phase, I got to break apart that attractive force, right? And so the stronger that force is, the more difficult it is to do, and the lower the vapor pressure, right? So molecules with strong intermolecular forces will have very weak vapor pressures. Molecules with very weak intermolecular forces will have very high vapor pressures. Okay? And we can see that in this chart here, where here we're looking at the vapor pressures of different molecules at different temperatures, right? Where you see things like water compared to diethyl ether or ethyl alcohol, okay? Right, the intermolecular forces of water are much stronger than ethyl alcohol. So at a given temperature, say at 40 degrees Celsius, the vapor pressure of water is lower than that of ethyl alcohol. right? Both ethyl alcohol and water have some hydrogen bonding, but water has 2 hydrogens attached to that oxygen. Ethyl alcohol only has 1. So water has like twice the hydrogen bonding, if you will. So it's got more stronger intermolecular forces. So that's why it has lower vapor pressure, while diethyl ether has no hydrogen bonding. And so that's why it's got much weaker intermolecular forces and a higher vapor pressure, okay? We'll note here the line that's associated with the boiling point of these different molecules, right? And this is telling us what about the boiling point? When does a substance boil, right? Right, that line's indicating normal boiling point. 760 torr is equal to how many atmospheres? Anyone have an idea? Yeah, 1 atmosphere, right? So it's 1 atmospheric pressure, right? So that's the pressure that is, say, in this room, right? And so you notice in this chart, right, that line is indicating the boiling point, meaning that these things boil at that line. And so what's happening at that line? We have atmospheric pressures at that line. And what happens with the vapor pressure of those substances? They are greater than, less than, or equal to atmospheric pressure at these points. They're equal, right? So it's equal to each other. So for example, water at 100 degrees Celsius, its vapor pressure equals that of atmospheric pressure, 1 atmosphere, and so it boils at 100 degrees Celsius, right? While diethyl ether boils at 34.6 degrees Celsius, because at 34.6 degrees Celsius, its vapor pressure equals atmospheric pressure, right? So liquids boil when their vapor pressure equals the atmospheric pressure, okay? Try to play this video real quick, show you how you can get water to boil at much lower temperatures as long as you.
In this demonstration, I am taking water that's in ether,
Let me,
and it has a thermometer.
I'm gonna mute that guy, but right. So I'm gonna fast forward in this video here. But what he's doing is he's slowly lowering, right? So here he has water in this container, right? The temperature of the water is roughly 20 degrees Celsius. I'm gonna make that video larger, right? It's 20 degrees Celsius, but you put this container of water in a vacuum and he's slowly reducing the atmospheric pressure. He's slowly sucking out air from this vacuum, reducing its atmospheric pressure. And you can start to see little bubbles forming in the water. So eventually you get this very vigorous boiling occurring at 20 degrees Celsius, right, for this water. And the reason that's boiling so vigorously is just because it has reduced the atmospheric pressure, the pressure on over the water, and so now it's able to boil at a much lower temperature, right? So in this video, all that's being done, right, in this video, all that's being done is we're lowering the 760 torr to say like 200 torr, and so now all the vapor pressure of water needs to do is reach, 200 torr, and it'll start boiling, or in this case, he reduced it down to, I don't know, a couple of torr or something like that in order to boil it at roughly 20 degrees Celsius, right? Point being, right, is that if you decrease the vapor pressure, that will decrease the temperature in which, decrease your external pressure, right? Your atmospheric pressure will decrease the temperature in which your substance boils. That's why water boils at a lower temperature at the top of a mountain, right? People who cook at high elevations need to potentially compensate the time of cooking because of the fact that the water that's boiling is not at as high a temperature as at sea level, right? So question here, would humidity impact that boiling temperature and vapor pressure? No. So all that really matters is the total pressure that's exerted on your liquid, okay? So it doesn't matter if it's water, vapor, or oxygen, or nitrogen, or argon, or whatever type of gas. that's sitting over that liquid exerting that pressure. All that matters is there's some pressure pushing on that liquid, keeping it in the liquid phase, right? And it's only when you increase the temperature enough to where its vapor pressure pushes back at the same amount as that's being pushed on it does it start to boil. Yeah, so liquid boils when its vapor pressure reaches 1 atmosphere, which is very true. That's correct. Vapor, right? And if you reduce the external pressure below 1 atmosphere, then you can get something to boil at a lower temperature. And it's just that it requires a lower temperature to reach whatever that lower vapor pressure is. So does boiling have the same properties like killing germs? No, it does not. So in this video that had water boiling at 20 degrees Celsius, it would not kill off any germs because what's killing the germs in boiling water is the heat, right? It's the fact that you're cooking these things at such high temperatures that it destabilizes their cells and breaks them apart and kills them, right? So boiling water at 20 degrees Celsius would not kill any germs. And then there's another question here, right, about how pressure and temperature are related, right? Right, and they're proportionally related. So, right, there's a statement here that temperature and pressure are proportionally related. This is very much true for a gas. For an ideal gas, right, we have our ideal gas law, PV equals nRT. So pressure and temperature are proportional to each other, okay? But it's not necessarily true for a liquid, right, or a solid. Right, and basically ideal gases assume no intermolecular forces. You have to use equations of states for real gases. I don't know if they ever talked about van der Waals gases or things like that in 1341, but real gases that include intermolecular forces in their relationship between pressure and temperature and things like that. It's not a direct proportionality, and the strength of those intermolecular forces affects that relationship between pressure and temperature. And it's not just, you know, PV equals nRT. Okay. Yeah. So that well, so for something to boil, and so the final kind of part of that question is related with something boiling, right? You have to break the attractive forces, but you do have to break the attractive forces for something to go from a liquid to a gas phase. But again, even water at room temperature, right? If I had a glass of water sitting at a table here in class, that water would be evaporating, and there would be water molecules going into the air, and eventually I leave that water here long enough and it's going to evaporate all the way away because, right, some molecules do have enough energy to break those intermolecular attractions to break apart into the gas phase. And that has nothing to do with necessarily boiling, okay? When a substance boils, it just means that those gas particles start forming even within the liquid, and not just at the surface of the liquid, but within the liquid itself. And that's how you start to get the bubbling going on in the liquid, and that's why it starts bubbling and, you know, creating all these bubbles in the liquid, is because it's not just at the surface that you start having molecules go into gas phase. You now have molecules within the liquid going into the gas phase, and that is where the bubbling comes from. Okay. All right. So now let's rank these compounds by increasing vapor pressure. Okay. So I have 1, 2, 3, 4. Yeah, 4 different compounds here. I want to know what has the highest vapor pressure, right, and what has the lowest, right? So lowest to highest. Okay. As we talked about, compounds, right, with stronger intermolecular forces have lower vapor pressures, and compounds with weaker intermolecular forces have higher vapor pressure. Okay? So out of these 4 molecules, which one is going to have the strongest intermolecular force and thus lowest vapor pressure? H2O, right? H2O has hydrogen bonding, right? That's one of the strongest intermolecular forces that exist, right? oxide's ion dipole, but there's no ions here, so that none of these have ion dipole forces, right? And so H2O has the weakest vapor pressure, okay, which is then going to have the second weakest, if you will, or you know, next strongest intermolecular force. So let's think about intermolecular forces here. CCl2 is going to have what type of intermolecular forces? Dispersion forces, right? Because chlorine bonded with another chlorine is not a polar bond, so there's no dipole-dipole. So it's just dispersion. NCl3 is going to have what type of intermolecular forces? Dipole-dipole, right? Because the nitrogen-chlorine bond is polar, and it's not symmetrical if you draw out this molecule, right? NCl3 would look like this. You'd have these polar bonds, right? All pointed kind of away from the nitrogen. I have this net dipole moment pointing down, if you will, okay? And so NCl3 is going to have dipole-dipole interactions, and then C16H34, just dispersion interactions. Anytime you see these big hydrocarbons with no oxygens or nitrogens floating around in them, then it's just dispersion interactions, right? So H2O's got the strongest intermolecular forces, weaker vapor pressure. Next, it's NCl3, which has dipole-dipole interactions, which are stronger than dispersion. And then you have Cl2 and C16H34 that both have dispersion intermolecular forces. Which one of these is going to have stronger dispersion intermolecular forces than the other?
The C16H34 because it's
Yeah.
larger.
Yep, exactly. C16H34 is a much larger molecule, so it's going to have stronger intermolecular forces. And the weakest is CCl2. So CCl2 has the highest, largest vapor pressure, right? Out of all four of these, H2O is the weakest, right? Right, ordering these from lowest vapor pressure to highest is H2O, then NCl3, then C16H34, and then finally Cl2. Questions? All right. So just in the label, these phase diagrams. Okay. Right. So what is going to be in this upper region here? What phase is here at low temperatures and potentially high pressure?
Solid.
Solid phase. What's going to be down here?
Gas phase.
So this one's gas, and this guy is liquid phase, right? These different lines represent what are called phase boundaries, right? These are just phase boundaries. So if I go across this phase boundary as that arrow is showing, what am I doing? What type of phase transition is this?
You're melting or
Yeah, melting or fusion,
fusion.
right? Yep, exactly. Fusion, melting. That's the type of phase transition that's occurring as I go from a solid to a liquid, as I traverse this boundary, right? These phase boundaries, at these phase boundaries, I have both solid and liquid existing in sort of equilibrium, okay? So, right, and it's when you go across the boundary that you undergo melting or vaporization or things like that, right? This point here is called what?
Triple point.
The triple point, right? This is the triple point. That's where all three phases coexist. Solid, liquid, and gas exist in equilibrium with each other at the triple point. And then this kind of point out here where the phase boundary between the liquid and gas end is the, starts with the C, critical point. Yep. Critical point, right? Our critical point, right? And that is our phase diagram. Any questions? How kind of drawing these phase diagrams? Right. So this phase diagram does not represent the type of phase diagram that you'd see for water. Anyone know what differs in this phase diagram for water? If it's, I'll give a hint, it's one of these three lines.
Oh,
Yeah, this
that-
one goes
yeah,
up.
that first one.
Yeah, this top line here goes up and to the left for water, and that's because for water, right, the solid is less dense than the liquid, which is one of the only compounds, I don't know if it's the only, but one of the very few compounds that exist that do that, right, which is again why ice floats in water, right, why there are icebergs, right, and there's giant things of ice floating on top of water, right, because of the fact that it is less dense than water. Right? So it makes the world go round. All right. So what phase transition occurs when you go from the state at point G to the state at point H? Is it going to be melting, boiling, sublimation, condensation, deposition, or freezing?
Sublimation.
Yep. Because we're going from a solid at the phase at point G is a solid. The phase at point H is a gas. That solid to gas transition is sublimation, C. All right. And then question here, right? Do you have a glass of pure water, right? You start boiling it, the bubbles that are forming in that water and reaching the surface are composed of what? Air and water, carbon dioxide, or just water?
Isn't it water?
Yep. So it's just going to be water here, right? Because right inside that water, that liquid water, you just have water, right? Those bubbles that are forming in the water are forming because liquid water is going into gas phase, right? It's going into the gas phase within that solution and then bubbling out of the surface and then going into air where then it mixes with the air and so on, right? But within the pure water itself, right, the bubbles that form underneath the surface are composed of just water, right? Assuming it is just pure water you got there. Okay, so D here, just pure water. All right. So last example we'll kind of go over for today is related with these heating curves. Right, this is related with these phase transitions, related with hopefully this equation or form of this equation you saw in 1341. If anyone here saw something like this, heat related to change in temperature and a T capacity, right? Hopefully saw that in the lab as well. It's a very common type of lab with like calorimetry and such. Okay. Right. So, right, we talked about these phase changes, these phase diagrams, right? And we can talk about the heat required to go from different phases and heat substances from one phase to another and so on. Okay. And so when you do change the temperature of some substance, you have to give in heat, Q, right? Heat. And that heat that you have to provide is related to that change in temperature. it's heat capacity, and then how much stuff you have, right? So in this case, the number of moles, and here's the number of moles, right? If you go a phase transition, right, the energy required, the heat required to do that phase transition is just the enthalpy of that transition times the number of moles of stuff that's undergoing that transition, right? The more stuff I'm undergoing a phase transition, the more energy it requires to cause that transition to occur, okay? Right? And the values of these enthalpy of transitions and these heat capacities are related with the strength of the intermolecular forces. The stronger intermolecular forces, the larger these values are for a given substance. Okay? We won't go into any type of relationship and how to predict that, but just as a general trend, heat capacity and this enthalpy of transition are greater for systems and molecules that have stronger intermolecular forces. Okay? And so we could ask a question like this, okay, is let's say, right, I have ice that I put in my water, right? I have 2 moles of ice, and I have 50 moles of water in my glass. The ice, which is at 0 degrees Celsius originally, melts and actually reduces the temperature of the water to 8 degrees Celsius. So it goes from 0 degrees Celsius to 8 degrees Celsius. Okay. And the question is, what is the enthalpy change or the heat exchange in this process? Okay. Given the enthalpy of fusion of water is 6 kcals per mole, and the molar heat capacity of water is 14.4 kcals per mole. Okay. So I'm going to hop back and forth real quick. But this is sort of related with these heating curves, right? Where you have the x-axis here is heat that you're providing. The y-axis is your temperature. You have some solid that you're heating up that undergoes a phase transition to a liquid that you then start heating, which undergoes a phase transition, then to a gas that you just keep on heating, right? And this phase transition, this is your fusion or melting, right? And then this here is your vaporization, right? Right, these phase transitions, right? And so in this problem, I have some solid at the temperature in which it melts, right? And I undergo this transition here, and then I heat up that substance to some temperature, some final temperature, which is, what is it, 8 degrees Celsius, right? And so I'm wondering, what is the total Q, right? Wait, what is that total amount of heat that had to be transferred, right, to cause that transition? Okay. And so how you do these heating chart problems, right, how you solve this is we just break things up into different steps, right? We potentially have Q for, right, for heating a solid, right? There's Q for fusion, for melting, right? Q for heating a liquid. Oh, on there, right? Q for vaporization, and Q for heating a gas, right? These are all the potential types of heat changes that can occur, right? By heating a solid, a liquid, or a gas, and undergoing these phase transitions from a solid to a liquid or liquid to a gas, right? In our case, we just have these two things going on, okay? So we only need to worry about these two things, right? And again, for any phase transition, the Q is related to the enthalpy of that transition times the number of moles, okay? And then for heating, right, that Q is related with the number of moles times the heat capacity times the change in temperature, right? So in our case, right, what we have, we have 0.2 moles, right? That is going from a solid to a liquid, right? Because it's my ice at 0 degrees Celsius, right? Going from a solid to a liquid. So the heat required for that is just that 0.2 moles times that enthalpy of fusion, right? And then after that, right, I now formed a liquid, right, at 0 degrees Celsius, right? The degree symbols over the C, right? So 0 degrees Celsius, okay, right? And then I take my liquid and I heat it up to 8 degrees Celsius, right? I now take my liquid and I go from 0 Celsius to 8 Celsius, right? So the heat for that process is related with the number of moles, which is 0.2, times the heat capacity, times that change in temperature, which is going to be 8 Kelvin. Okay. Conveniently, right, if I increase temperature by 8 degrees Celsius, it's the same thing as increasing the temperature by 8 degrees Kelvin. Okay. If I go back to the slide here, that's kind of worked out, typed up a little bit more. Right, so again, step 1, I melt my ice, right? My heat of fusion is 6 kcals per mole. So that's 6 kcals per mole times 0.2 moles to undergo that transition to give me 1.2 kcals. Right, I then heat my water from 0 degrees Celsius, 8 degrees Celsius, right? Given the molar heat capacity is 4.4 kcals per mole. That's just 0.2 times 14.4 times the change in temperature 8, which gives me 22.04 kcals per mole. I just add those two things together. Oh, I didn't add that correctly whatsoever. That should be 24.24, not 14. Sorry. Right, but that's 24.24 kcals per mole is the total heat change, right, in this process. Okay. All right, so that is the end of chapter 12. You will have homework for chapter 12 that's due on Monday next week, right? That's on sapling. If you're having issues getting your sapling accounts, linking it with, right, or adding my section or things like that, please let me know, and I can try to do my best to help out. I will be posting a quiz soon on chapter 12 that will be on Canvas that you will also need to complete. And soon I'll have the chapter 13 videos up online. Okay. I'll see those of you here in class again on Wednesday next week. Those of you online, I'll see most of you on Monday. And that's it for today. It should be in Kelvin. Now, because converting to Celsius, you add 273 or whatever to Celsius, right? And so when I take the difference in those temperatures, I have 0 plus 273 minus 8 plus 273. And so those 273s just cancel with each other. So it's just an 8. Okay, so that is kind of convenient, but technically, if we want to make sure we're doing things right, I would convert to Kelvin first and then take the differences. But yeah, it should be in Kelvin. Mm-hmm.
About like the practice problems we've been doing. So like I watched the lecture you did, I think so I'm just kind of confused on like how you look at like compounds and stuff and just like like experimental like without like drawing everything on.
I mean, basically, yeah, a lot of it is just practice. I mean, that's why I tried to do a lot of examples today. A lot of it is just practice and drawing it out, and really kind of drawing it out and understanding what the structures are. You know, for example.
Yeah, for like the first like 3 or 4 questions, I was like, how the hell did like, because I understand like the like dipole
Yeah, what the
and that stuff,
forces
but it's
are.
just like seeing
Yeah.
carbon and like associating that with like the dipole stuff. Like,
Yeah, yeah. And so again, for like this first set of questions,
oh yeah,
Um,
this one was one that I was like, how did you like?
yeah. So I know, for example, H2 and Ne don't have dipole-dipole forces because H2, the bond isn't polar because they're the same atoms. And then Ne, there's no bond, so it can't have, so there's no dipole-dipole in there. You have to have a polar bond, and it has to be non-symmetric, right? And so CO has a polar bond, and it's not symmetric because, right? I mean, symmetric is like the idea if you flip it around on itself, does it look the same, right? And CO doesn't, right? BaCl was, a little trick in here because this is just an ionic compound, so it's not even intermolecular forces, it's intramolecular forces, right? That you learned about in 1341. And then HF, it technically has dipole-dipole interactions, but whenever we have hydrogen bonded with fluorine, oxygen, or nitrogen, it's just hydrogen bonding, and we don't even worry about the weaker stuff. We just say, okay, it's hydrogen bonding. That's it. For this one, I put up a lot of these, because like this linear molecule, right? You need to know that this is, need to have an idea that this is linear to understand that it's going to have no dipole-dipole interaction because those polar bonds cancel each other, right? Right. And if we don't have that structural knowledge, then I would say, oh yeah, dipole-dipole, carbon and oxygen have polar bonds. And so yeah, so I try to put up the examples of the typical type of structures that we see in the class, right? And so, CO2 is a very common linear molecule that wouldn't be polar. There's not very many other ones like CO that I talked about. That's polar, right? HCl, HI, like, a lot of other linear molecules are all going to have dipole-dipole interaction. CO2 is, at least off the top of my head, the one I can think of that doesn't. These carbon bonded with 4 same atoms are always going to be just dispersion of dipole-dipole because they're always bonded physically. There's 4 of them, right? But then like, where's the CH3Cl, that one has dipole-dipole because chlorine is not the same as hydrogen, right? But the CCl4, right, that doesn't have dipole-dipole because all the 4 chlorines are bonded the same. They're bonded symmetrically on the carbon, right? And like these guys, if you just see carbons and hydrogens bond together, that's just dispersion. But yeah, so it's, I feel like it's, and these, I don't have a better way, but like, without drawing out all the structures, right, it's basically practice. Is what it comes down to, and that's why I was trying to put a lot of these to try to get as much practice.
All right, thank you so much.
I have a couple of questions.
Okay. Yeah.
Okay. So I asked a question about. Oh wait, are you ready for me?
Yeah. Just one second. Yeah. Go for it.
Okay, so I asked a question about how pressure affects it earlier, and you answered it, but I'm still a little confused because I know, like about the relationship and Pivner and all that good stuff, but like I know when you add more temperature to like a liquid, right? Like because it's an endothermic process, the bonds break or the intramolecular forces break to make it into a gas, right? And then, but pressure, like if you increase the pressure, it boils at a lower temperature. So does pressure only affect, like, because it's a condition, so does it affect the, like, how does it affect the bonds? Or like the attraction?
So,
I understand that like temperature adds energy, which like makes it move, like, but pressure doesn't add, unless it.
So pressure doesn't necessarily add energy, but what pressure can do to, say, like a gas is as you increase the pressure of a gas, if it's a real gas, so ideal gases would never form a liquid because ideal gases have no intermolecular forces. But real gas, real system, as you increase the pressure, you're squeezing the molecules closer together with each other, making them on average be closer to each other, right? So an increased pressure is associated, at least with a gas, with a decrease in average intermolecular distance, which is typically going to mean that the closer these things are together with each other on average, the stronger they feel those intermolecular
So
forces.
is it like the kinetic like energy? Like I forgot when we were learning this, but it gives it more opportunity to like I forgot the wording, but more opportunity to collide
Attract each other.
and bond. And yeah,
Molecules, have more opportunity in the gas phase to attract each other and form a liquid, right?
and
Increase the
collide.
pressure of the liquid, right? If you increase the pressure push on a liquid, you can make it form a solid, and that's mainly for most things, not water, but any other compound for the most part. If you increase the pressure on the liquid, it's going to form a solid. The solid is less dense, and so the molecules rearrange themselves to try to get into the best packing way possible they can to alleviate this increased pressure on them, and that's what causes it to form a solid, is because it's trying to reduce the effect of this pressure as much as possible, and so the molecules rearrange themselves into kind of the structure they would form in a solid, for example.
Okay, that makes sense. Thank you.
I have a question.
Yeah.
You might have mentioned this already. It's just about the quizzes. Will there be like a specific day each week they're due?
Yeah, so I'll have a due date. I think this first one, I'm trying to decide how exactly I'm doing these because I'm going to probably for this first one just pick a day to have it due and things like that. I might try something where I have it on like Friday during normal class period because people shouldn't have class then and things like that. I might be able to do it. I don't know. I'm trying to figure out exactly when that is, but they will be on Canvas and there will be a due date. And I mean, this first one might be slightly different in terms of when it's due and things like that than the other ones because it's, going to be due by sometime early next week. And so I'm going to put that up there and I'll put a due date. But typically how it'll work is you'll have some range of time to take it. I probably won't make it just a few hours since it's not during the regular class time, but I'll have some probably like a day to take it, and when you start it, you'll have, say 20 minutes or something to finish or 30 or however long I kind of give you, but you have some amount of time once you start to finish the quiz. And then, the quiz is over. And it will be, but again, it will be on Canvas and you'll have like something like a 24-hour period to log in and take the quiz. I just don't know exactly what day that's going to be. If I'll try to make it this Friday or if we'll make it a day over the weekend or how we'll do that. But yeah, it won't be just like a 1 hour window or something like that you'll have. You'll have like a 24-hour window. Yeah. Does that answer your question? Oh, yes. Yeah.
So I sent you an email like 1:55, which you can now ignore because I'm here in case you did
Okay.
see it. I was 30 minutes late for class today, thanks to some poor drivers. So I just wanted to make sure that like watching the video gives me.
Yeah,
Kind of
you'll
like handouts or anything.
Yeah, I mean, there was just, I don't know if you saw this when you came in.
Oh, no, I stayed in the hallway because I didn't want to interrupt.
Oh, no,
I
I'm
joined
so
the Zoom
sorry.
meeting.
Okay, yeah, you're welcome to, if you want to fill that out and answer that, either now or if you want to next week. I don't know. I mean, it shouldn't take too long if you want to
Okay.
sit down and attempt it. Again, all you have to do it, like to get full credit, you just have to put your name and an answer.
Okay.
So, yeah, so let me
Yeah,
just.
I definitely missed some of it. Like